Good afternoon, everybody. Gosh, I have missed this stage, this room, this event just about as much as anything else during COVID. And it is so good to be back across the Atlantic to tell you another story this afternoon. I'm so thrilled to be here. I don't even have words to tell you how excited I am. Like Mary said, my name is Nicholas Means. I'm VP of Engineering at SIM, where we're building access workflow tools for engineering teams, letting your team describe complex permissions and approvals in code using simple Terraform and Python primitives. We let you manage access requests via Slack and even allow engineers to conditionally self-approve their own access under certain situations, all with streaming audit logs, all in Git alongside the rest of your infrastructure as code to make you, your team, and your auditors happy. Now, if that sounds like something that you might be interested in, come talk to me. I'd love to tell you more. And thanks so much to everybody at SIM for holding down the fort while I'm here and for giving me the time to be here with you today. Now, before I get started, I need to give you a content warning, because this talk does contain the stories of 2 plane crashes, one of them pretty vivid. So if you're already a nervous flyer, this may not be the talk for you, and I will not be offended in the slightest if you need to step out now or at some point later in the talk. So don't even think twice about that if that's you. Now, if you were to follow me on Twitter, you would quickly learn that I'm occasionally into plane spotting, especially when I'm traveling. I love seeing planes that I've never seen before, like this weird little Avro RJ85 regional jet I saw at London City a couple years ago. This thing has 4 engines, the same as a giant 747 or A380, despite the fact that it only carries 100 people. Why does it need 4 engines? I don't know. Or this beauty that I saw yesterday leaving Prague. It's a Lufthansa A321, but it's in a beautiful retro livery. And I have a thing for old planes and old liveries. I love the way this plane looks, so I was excited to see it. But I also really like trying to identify planes from the ground. It's a bit of a game for me and some of my aviation-minded friends to spot a plane flying overhead and try to figure out what it is, and then pull out Flight Radar 24 and hold up the AR feature and see if we were right or not. And the first plane that I learned to identify really reliably was this plane, the 737. Now, the 737 is the most widely built commercial aircraft of all time, so these things are everywhere. And once you know the trick, it's incredibly easy to identify this plane from the ground. See the 2 tires poking out from the underbelly there? If you see that, and it's too big to be a regional jet, you're looking at a 737. So why am I telling you this? Why are we talking about plane spotting? Well, there's a really interesting reason that the 737 doesn't have rear landing gear door, that you can see those wheels from the ground. 737 was launched by Boeing in 1967, 55 years ago. Commercial aviation was still in its infancy, and airlines decided that they wanted a plane that would let them serve smaller markets. Up until then, they largely had larger jets that could fly into the big cities with their big, glitzy, modern airports. But a smaller airport might be lacking some of the amenities that they needed, like jet bridges and baggage handling equipment. And so they built the 737 low to the ground so that the ground crews could load and unload baggage without even a step stool, let alone a baggage conveyor. That low clearance is why the 737 doesn't have rear landing gear doors. There's just not room under the plane for the doors. And that lack of ground clearance, one of the earliest design decisions they made about this plane, has everything to do with the problem with the 737 MAX. Now, we got the first hint that there was a problem with the 737 MAX with the crash of Lion Air Flight 610 off the coast of Indonesia on October 29, 2018. This is the Boeing 737 MAX 8, registration number PK-LQP, that would operate Lion Air Flight 610 on October 29, 2018. In this picture, the plane is at Boeing's Everett, Washington customer delivery facility, getting ready for its maiden voyage across the ocean to Indonesia. And this was taken in August of 2018. And so if you do the math, this plane was about 2 months old on the day of the accident. It was essentially brand new. The captain for Flight 610 was this gentleman, Bhavya Suneja, an experienced pilot with over 6,000 hours of experience in the cockpit, most of it in the 737. In the right-hand seat was Harvino, who goes by just the one name, a fairly common practice in Indonesia. He was another experienced pilot with almost as many hours in the cockpit of the 737 as Suneja, so this is an experienced flight crew. Flight 610 was scheduled domestic service from Jakarta to Pangkal Pinang in Indonesia, departing at 6:20 in the morning and scheduled to arrive 50 minutes later. Now, the easiest way for me to tell you this story is in data. This is the transcription of the telemetry data from Lion Air Flight 610 from the Indonesian NTSC's accident report. And it tells a really clear story once you know what you're looking at. So let's walk through it. To get you oriented, the timestamps here at the bottom are all helpfully 1 minute and 19 seconds apart, really easy to comprehend. That's the result of them taking this flight and dividing it into 10 equal segments instead of just using minutes. The flight was about 12 minutes long. And let me add some better labels so that you can read them from out there as well. Those are kind of tiny. So that makes it a little easier to read the chart and understand what's going on. Let's start with the moment that the plane gets airborne. There's a couple of things that immediately indicate that this plane's got a problem. First of all, as soon as the plane's in the air, the pilot's stick shaker starts shaking. Now, this is exactly what it sounds like. It's a vibration motor attached to the pilot's yoke that literally shakes the yoke in the pilot's hands. And it's the aircraft's most urgent warning mechanism, the thing that it uses when it really needs to get the pilot's attention. And it would do this when the plane thinks that it's about to stall. Now, you may already know this, but we're not talking about the engines when we talk about stalling in an aircraft. We're talking about the wings and their ability to generate lift. When a wing is moving at too steep an angle or too slowly through the air, vortices can form on the top of the wing, and that disrupts the smooth airflow over the top of the wing. If you get into Bernoulli's law, you'll learn that smooth airflow over the top of the wing is the thing that actually generates lift for the wing. So those vortices are bad news. So when the airplane senses that it's at risk of this happening, it kicks on the stick shaker. But this plane has just taken off. It's flying smoothly. It's ascending from the runway. There's no problem. Why does it think it's about to stall? Even stranger, if you look at the graph up there, it's a digital graph. You can see that the graph on the pilot stick shaker goes from 0 to 1 when the stick shaker turns on. The co-pilot stick shaker right below it never turns on. If this was actually a stall, you would expect the stick shakers on both yokes to be going off, not just the pilot's. And the answer to why this is the case is a few lines down the chart. When we look at the angle of attack. Now, these lines are on the same axis. They should be exactly the same, but instead, the angle of attack indicated on the pilot's instruments is about 20 degrees greater than on the co-pilot's. So what is angle of attack? Well, when a plane is flying through the air flowing over the plane may not necessarily follow the nose of the aircraft. It can get off axis. And so angle of attack is a measurement of how the airplane is moving through the air. In a stall scenario, the airplane might be nose up, but instead of moving this way through the air, it's actually moving more parallel to the ground, or maybe even descending a little bit. And this is one of the ways that the plane knows that it's about to be at risk of a stall. The plane senses angle of attack with a vane like this on each side of the aircraft, each one feeding the respective side of the cockpit instruments that it's on. And so because the pilot's angle of attack sensor is 20 degrees off, it's only the pilot's stick shaker that's going off. Critically, if you look at this graph, you can tell that malfunction starts when the plane is still on the ground, and it lasts the entire flight. And so when the plane finally does take off, the plane immediately thinks that it's stalling, or at least on the cockpit, the pilot's side of the cockpit. About 2 minutes into the flight, Harvino asks Indonesian air traffic control for a vector to some holding point. Air traffic control asks him what he needs, and he tells them, well, we've got a minor control issue we need to sort out here. Crucially, he doesn't declare an emergency yet. They keep flying. A minute later, having reached their hold point, Captain Suneja becomes concerned about something else on the cockpit, the plane's flaps. Now, the flaps are the wing extensions that come out the back of the wing and help it generate extra lift at low speed. And Suneja was concerned about them because the plane was flying too fast to have its flaps extended. And so he retracts them. Almost immediately, when he retracts the flaps, the plane plunges 700 feet, a little over 200 meters, uncommanded. Suneja finds himself pulling back on a suddenly very heavy yoke, and he has a good idea what's happened. His aircraft is out of trim. And sure enough, there's a major nose-down change in trim reflected in the data. So let's talk a little bit about what trim is. And we'll do that by looking at the back of the 737. This control surface that you see at the back of the 737 is called a horizontal stabilizer. It looks kind of like a mini wing. And at the back of the horizontal stabilizer is the elevator. The elevator is the control surface that acts when the pilot pushes or pulls on the yoke. It's the thing that causes the attitude of the plane to tilt up or go down. But if you think about it from a pilot's point of view, it would be exhausting to sit there and pull back on the yoke all the way from 0 feet to 40,000 feet and to push on it all the way back down. So if you look at the front of the horizontal stabilizer here, you can see that there's a metal track. This entire mini wing can tilt up and down. That's what we mean by trim. And you can think of it kind of like cruise control for ascent and descent in the flight, so that the pilot doesn't have to sit there and push and pull on the yoke. Now, for some reason, the plane's auto trim had made a pretty dramatic adjustment to pitch the nose of the plane down, seen here in yellow. Soneja quickly provides a manual trim adjustment the other direction in blue, but a few seconds later, auto trim kicks in again to pitch the nose back down. Now, if any of you are pilots in this room, you know there's an unwritten rule in the world of aviation that when you make a configuration change to an aircraft and something that you don't expect happens, your first step is to undo that change. And so that's what Captain Soneja does. He immediately retracts the flaps. He doesn't understand why the auto trim's kicked in, but he extends the flaps again. He extends the flaps. He extends the flaps again in hopes that the auto trim will stop. And it does. There's still a few routine adjustments. Auto trim still kicks in, but no more dramatic drops. But Soneja's still thinking about those flaps. At this point, he's still intending on continuing this flight to Pankal Penang, and he knows he can't do that with the flaps extended. And so he retracts them again. And almost immediately, he's back to fighting the auto trim on the plane. Now, about this time, Captain Harvino gets on the radio to ask Jakarta Air Traffic Control for a return back to the airport. They grant the return, but there's a couple things that are strange about this interaction. First, Harvino still doesn't declare that emergency. And second, the air traffic controller, despite the plane's request to return, something you would almost only ever do in an emergency, doesn't ask him if he would like to declare an emergency. Now, this is critical because when a plane declares an emergency, they get priority routing back to the airport. They can land basically on whatever runway they request. The air traffic controller understands that it's an urgent situation and treats it that way. By not requesting that emergency, air traffic control is giving them vectors around other traffic in the area the whole way back to the airport, increasing Soneja's workload as he's just trying desperately to keep this plane in the air the whole time. Soneja would keep fighting the plane for the next 6 minutes, while Harvino scoured the flight manual for anything that might explain what was going on and how to fix it. For every auto trim activation, Soneja would counter with an equal burst of manual trim. And the trim, despite oscillating up and down, would average out to mostly even over the 6 minutes. You can draw a pretty straight line through that graph. And so at altitude, Soneja was having to fight like hell, and it would have been terrifying to be in the back of the plane, going up and down in 100 to 200 foot, 30 to 60 meter bursts. But he's keeping the plane more or less at an altitude of 5,000 feet. Finally, Soneja's out of options. He's not sure what else to do with this plane, so he gives the controls to Soneja. So he gives the controls to Harvino so that he can look through the flight manual himself and see if he can find something that might be causing the problem they're seeing on the flight deck. But he's so flustered that he forgets to tell Harvino what he's been doing to keep the plane level. The auto trim continues to activate. Harvino counters here with a few short bursts of manual trim the other direction, but it's not nearly enough to counter the auto trim. And in less than a minute, the plane has reached maximum nose-down trim. At this point, Harvino's heard on the cockpit voice recorder reciting a verse out of the Quran, asking God for a miracle. Soneja's pulling back on the yoke as hard as he can pull, trying to pull the plane out of the dive. But it's just too late. Flight 610 plunged 5,000 feet in 15 seconds, hitting the water at over 500 miles an hour, about 1,100 kilometers per hour, killing all 189 people on board. It was an absolute tragedy. The world understandably wanted to know what happened. But the other operators of the 737 MAX, well, they needed to know what happened. They needed to know if something like this could happen to their brand new 737 MAXs as well. And so 8 days later, Boeing would send its first message to the operators of the 737 MAX. But it doesn't say much, basically just that the early information about Lion Air 610 indicates that a malfunctioning angle of attack sensor caused an uncommanded nose-down trim. The only problem was that there, at this point, is no documented system on the 737 by which the angle of attack sensor can cause anything to do with the auto trim. Nobody knows why this would have caused the auto trim to kick in. And so this caused more questions than it answered for the operators of this plane. Boeing got so many questions that 4 days later, they sent out another memo to operators. This message contained the first public acknowledgement of the now infamous Maneuvering Characteristics Augmentation System, or MCAS. This is the system that was responsible for the uncommanded trim on Lion Air 610, and if you followed the 737 MAX story at all, you've probably at least heard of MCAS. So what is MCAS? Well, to answer that, we have to talk a little bit about the 737's engines. This is the original engine used on the 737, a Pratt & Whitney JT8D low bypass turbofan. Despite the plane's low clearance, you can clearly see under the wing that there's plenty of room between this engine and the ground. But the low clearance became a challenge as engine technology evolved. In the early 1980s, when Boeing wanted to update the 737's original low bypass turbofan with a modern, more efficient high bypass turbofan, they had to find a way to fit the much larger engine under the wing. This strange-looking, almost egg-shaped engine inlet was the result. So if you've ever wondered why a 737 doesn't have round engine inlets, this is the reason. This was the only way that they could get enough air into this engine and also maintain the level of ground clearance that they needed. They used the same solution in the mid-90s, 15 years later, to create the 737 Next Gen. In addition to upgrading the cockpit from analog to digital instrumentation, the 737 Next Gen squeezes a slightly more efficient high bypass turbofan under the wing using the same but not quite as dramatically flattened inlets. But the low clearance went from interesting engineering challenge to real problem in 2010. Because in 2010, that Airbus introduced the A320neo. Now the A320 is the 737's closest competitor. It carries the same 180 or so passengers on the same regional routes. The Neo, short for New Engine Option, was the first major revision of the 320 since its launch. It incorporated new CFM LEAP turbofan engines with a much higher bypass ratio, resulting in nearly 20% fuel savings versus the older A320, and critically, versus the 737 Next Gen. Now, Boeing had long disregarded the competitive threat posed by Airbus. They thought that their planes were poorly made and that passengers didn't like flying on them. But they hadn't paid attention to the progress that Airbus had made in the intervening years and how the quality of the aircraft they had produced had gone up so dramatically. Boeing looked at this plane not as a threat. They were planning on designing a new plane from scratch for the 180-seat market. And they assumed that their current customers would continue to be loyal to Boeing, that they would continue buying the 737 Next Gen until this brand new plane was ready. Boeing CEO James McNerney got a rude awakening early the next year, though, in a phone call from then American Airlines CEO Gerard Arpey. American was planning to make its largest ever aircraft purchase, 400 planes in all, to replace its aging fleet of McDonnell Douglas MD-80s. McNerney thought the deal was a shoo-in for Boeing because American's entire modern fleet was all Boeing. That was the only thing that they had bought. So it was a shock when McNerney told them, or when Arpey told him, that the first 200 planes would be a mix of A320s and A320neos from Airbus. It was a real kick in the pants. But there was good news. Boeing could still compete for the other half of the order, but American wanted the same fuel economy as the 320neo, and it wanted it on the same 5-year timeline that Airbus had promised. So to fully understand Boeing's response, we need to go back further to 1997 when Boeing acquired McDonnell Douglas, another American aircraft manufacturer. Boeing, led by CEO Phil Condit, had long been an engineering-driven company with engineers all the way to the top. Condit himself was a trained aeronautical engineer. McDonnell Douglas, on the other hand, was led by Harry Stonecipher, a graduate of Jack Welch's GE. And if you know anything about Jack Welch and GE, the phrase maximizing shareholder value is probably popping into your head right about now. Stonecipher came into Boeing as president and CEO after the merger, and he made his influence quickly felt. Boeing came much more focused on margins and on stock price. And Stonecipher also convinced Condit and the Boeing board to move Boeing headquarters from Seattle to Chicago. And he did this as a means of culture change, to give the executives making decisions at headquarters some insulation from the engineers that they might be making mad with some of those decisions that they were making. When Condit resigned as CEO in 2003 and Stonecipher took over after him, Stonecipher had this to say in an interview. When people say I changed the culture of Boeing, that was the intent, so that it's run like a business rather than a great engineering firm. Now, this sounds pretty innocuous on the surface, but this culture change had resulted in an increasing win-at-all-costs environment inside Boeing. McNerney, who took over from Stonecipher in 2005, was cut from the same GE cloth. And at this point, Boeing's 787 Dreamliner was suffering from manufacturing delays and battery problems, so the 737 was the only plane Boeing was delivering in any volume in the early 2010s. Boeing stock was already down because of the media coverage around the problems of the Dreamliner. And Americans' defection to Airbus would create further negative pressure on their stock price. McNerney was terrified that other airlines might follow Americans' lead and order Airbus planes as well, and he wasn't about to let that happen. And so 3 months later, the 737 MAX was born. Designing it was a frantic project inside Boeing, with engineers working at about double their normal pace. Boeing made some aerodynamic improvements to the plane, and they expect the exact same CFM LEAP engines as the 320neo. And they ended up being able to match the 320neo on fuel efficiency. And their plan worked. American did place the other half of its order with Boeing, but with a condition. Americans said that the 737 MAX had to be type rated with prior versions of the 737, meaning that pilots wouldn't need any additional training to be able to fly it. And this makes sense if you think about it. They're already spending a lot of money to train a big chunk of their pilot workforce flying these new 320s and 320neos that they've just bought. Part of the reason they would buy the other half of the order from Boeing is to not have to train the other half of their pilot workforce and to be able to continue to use that knowledge. Southwest Airlines, the largest operator of the 737 in the world, also placed an order for 737 MAXs. They were excited about the fuel efficiency as well. But they made the same condition as American and made it even stronger. They insisted that the contract include a $1 million per aircraft rebate if pilots needed simulator training to be able to fly the 737 MAX. Now, the CFM LEAP engines used on the NEO and the MAX, they get their efficiency from a higher bypass ratio, meaning there's more space around the compressor core of the engine, more air can flow through. You get more airflow for the money that you spend on fuel. And that means that CFM LEAP engines are bigger, a lot bigger. Now, this common type rating wasn't a challenge for Airbus because they've got plenty of clearance off the ground. They could just swap in a new engine, change a little bit about the software, everything was fine. But because of how much lower the 737 sits to the ground, it wasn't nearly so straightforward for Boeing. Even with the sculpted inlet, the LEAP would be too large to fit under the 737's wing. So what do you think Boeing did? They worked around it. You can see here that instead of trying to fit the engine under the wing, they just moved it out in front of the wing. That gave them all of the room that they needed for the bigger engine. It's a clever workaround, but like most workarounds, it comes with drawbacks. They discovered a problem in early wind tunnel testing where in a steep banking turn close to stalling, the plane didn't have the same control sensation, the same pressure on the yoke as previous versions of the 737. Now, this is a scenario that a commercial aircraft with passengers aboard will almost never find itself in, but it is one that's required by certification. And not matching that control feel would mean that the 737 MAX would not qualify for that crucial common type rating. Now, some engineers in Boeing at this point advocated for an aerodynamic fix, some actual changes to the physical aircraft, but that would have added months to the project. So instead, they reached for a new software solution they just deployed on this plane, the KC-46 tanker. MCAS was actually created for the KC-46, and its original purpose was as this plane offloaded its fuel cargo, the center of gravity would change. In order to make it where the pilots didn't have to think about that, didn't have to change the way they were controlling the plane as they offloaded fuel, they introduced MCAS to make the plane fly the same as its center of balance changed. On the 737 MAX, MCAS would adjust trim by just 0.6 degrees nose down in that one specific scenario, just enough to mimic the control feel of prior 737s. And it was at this point that Boeing made a critical decision. The U.S. Federal Aviation Administration, the body responsible for certifying new aircraft in the United States, has long delegated non-critical parts of aircraft certification to the manufacturers themselves. This is so the FAA can focus its scarce resources on things about the plane that are truly safety critical. Because of how rarely MCAS was expected to kick in and how in this one specific scenario, Boeing categorized potential MCAS failures as hazardous, but not catastrophic. And I use the air quotes because those are the technical legal terms. That distinction allowed Boeing to self-certify the feature. And it also let Boeing drive its operation with a single angle of attack sensor, rather than the redundant inputs that would be required for a system categorized as catastrophic. But Boeing's test pilots would find another problem with the 737 MAX once they actually got it into the air. We talked earlier about stalls, when the wing of the plane loses lift. Now, in the previous version of the 737, in a low-speed stall, it was a pretty dramatic event. There would be lots of vibrating buffeting that occurred leading up to the stall, and the nose of the plane would dip quickly by 30 degrees. The MAX, because of its further forward and more powerful engines, it would still vibrate a little bit getting close to stall, and then it would just so gently nose down by about 10 degrees. Not very noticeable at all. Now, this was a critical difference in the way the plane handled. And it would absolutely cause the plane to not get a common type rating. And so Boeing reached for MCAS again. But this time, instead of 0.6 degrees of activation, they would need 2.5 degrees of nose-down trim in order to get this plane to behave like previous 737s. That's 5 times as much input. Again, it worked great. It made the MAX feel almost exactly like previous generations. But because MCAS had already been declared non-critical, and this activation was expected to occur only at low speeds when pilots would have plenty of time to react to it, Boeing decided against updating the safety categorization it had made with the FAA as part of the plane certification. But one critical thing that neither Boeing nor the FAA seemed to have thought about was the possibility of MCAS activating repeatedly. The maximum adjustment of trim on any 737 model is 4.7 degrees in either direction, up or down. And so if you do the math, it would take just 2 MCAS activations without any contrary input from the pilot to hit maximum nose-down trim on this plane. What's more, MCAS would only give the pilot a 5-second break after a manual trim adjustment before MCAS kicked in again. They would adjust trim, the plane would wait 5 seconds, and MCAS would go again, and they would be pointing down again. All of Boeing's analysis was based on a single activation because Boeing assumed a pilot would be able to spot and address an erroneous activation in 3 seconds. And the reason for this assumption is that MCAS is remarkably similar to another control problem that pilots drill for on a regular basis, runaway trim. In a runaway trim scenario, the plane's trim goes all the way to one extreme in one fell swoop, and it doesn't stop. When this happens, these 2 wheels start spinning. These are the manual trim adjustment wheels, and you can see the white markings that they have on them. Those white markings are there so that you can see them spinning. They're also not quiet. In a 2.5 degree MCAS activation, these wheels would spin about 40 times, and they would make a lot of racket doing it. So it's pretty hard to miss that this is happening. And when it does happen, recovery should be pretty straightforward. First, the pilot turns off the 2 electric stabilizer cutout switches. This disables the electric trim control in the plane entirely, and it lets the pilot revert back to manual trim control, so the plane will no longer make any changes to the trim. Second, the pilot would pull back on the yoke to get the plane level again. And once the pilot got the plane level, they would use the manual trim wheels to retrim the plane and get it to where it was flying level, and they would slowly let off on the yoke pressure as they did it. Well, we know Captain Sunajan knows he had a trim problem on Lion Air 610 because he repeatedly countered MCAS's trim inputs with manual trim inputs the other direction. So why didn't he or Harvino hit the trim cutout switches? Well, pilot and aviation journalist William Longovicia would argue in his New York Times article that it comes down to pilot training. Specifically, because of the rapid rise of global aviation, there are more flight decks than pilots to fill them. And airlines around the world, including Lion Air, are having to scale up their own pilot training academies in order to train enough pilots to keep up with the growth of their airlines and the demand for plane travel. Longovicia's assertion is that pilots trained in some of these academies learn by rote rather than experience, and they graduate knowing how to do the steps to fly a plane, but not what to do when they get outside of a certain set of predefined situations. The stunning 95% graduation rate of Lion Air's training academy would point to this lack of rigorous training. As would the fact that Indonesia, with one of the fastest growing aviation sectors in the world, has 15 times more passenger deaths per million flights than the global average. Now, the global average is a tiny, tiny number, so this is still very small, but is a statistically significant difference in safety from the aviation industry and the rest of the world. And so the theory goes that because the situation presenting itself to Sunajan and Harvino didn't precisely match anything they'd been trained on, because MCAS pulsed on and off instead of being continuous like runaway trim, they didn't have the base aviation knowledge or instincts to know what to do in this situation. The situation would repeat itself less than 5 months later on Ethiopian Airlines Flight 302. Now, notably, this is after Boeing published the bulletins about MCAS, so the flight crew on this plane would have known about the system and the situations in which it activates. Again, a malfunctioning angle of attack sensor meant that the pilot stick shaker was vibrating almost from the moment the plane left the ground. But in this case, the flight crew actually did hit the stab trim cutout switches. They did turn off the electric stabilizer control. The problem was, by that point, MCAS had already deflected their trim so much that the aerodynamic loads on their horizontal stabilizer were such that they couldn't adjust trim by hand. There was too much force. So they turned the electric trim back on, and before they could manually adjust the trim, MCAS had kicked in again, and they were so close to the ground that they crashed, again killing everybody on board. Well, the second crash led to the worldwide grounding of the 737 MAX fleet and scenes like this of undelivered 737 MAX planes sitting at the Boeing plant in Renton, Washington. So why did this happen? Where do we get to point our finger? Who can we blame for this situation? Was it Boeing's fault for the way they added MCAS to the 737 MAX? Was it the FAA's fault for not being closer to the certification process? Was it the pilot's fault for not recognizing an obvious situation on the cockpit that they should have been able to diagnose and fix? or the training academy's fault for not training them better so that they would be able to recognize that? Well, if you know anything about complex socio-technical systems, you know that there is never one root cause, ever. In her fantastic book, Thinking in Systems, Dr. Danella Meadows gives us some great tools to pick apart this situation using the formal discipline of systems thinking. In the book, Meadows introduces the concepts of stocks and flows and feedback loops. Stocks are the foundational units of a system. You can think about them as the things that you can measure. They move slowly, taking time to react to changes in the system. Flows are the things that increase or decrease those stocks. You can think of a stock somewhat like a reservoir, and the water level in the reservoir is your stock. There are things that flow into the reservoir, like rain and snowmelt, that cause the level of that reservoir to go up. There are things that flow out of that reservoir, like agriculture use and evaporation, that cause the level of water in the reservoir to go down. And then there are feedback loops that affect the rate of change. So things like a drought increasing agricultural usage and agricultural need for water, causing the amount of water to go down in that reservoir faster, speeding up the rate of change. Now, this modeling rabbit hole can go pretty deep, so I'm going to keep it as simple as I can, famous last words. And the stock we're going to consider in this system is safety. Now, it's hard to quantify, but if you think about it, the reservoir analogy sort of makes sense in that there's things that make safety in the system go up and things that make safety in the system go down. The clouds represent the boundary of our system. We're not going to think about where safety comes from and where safety goes to in the system because that's a complex philosophical question that we just don't have time to get into this afternoon. But we are going to think about what affects the rate of increase and decrease of safety in the system. And the reason for this is because rather than being static one-time events, the things that affect safety in the aviation system tend to be things that have longitudinal effect. They tend to be things that are cumulative over time. And the goal in all this is to keep the rate of increase of safety in the system high enough to make up for any decrease in safety and maintain the margin of error in the system. That means little mistakes don't end in big catastrophes. Let's start with pilot training. We know that the desire to increase safety in the system positively drives the quality of pilot training, and that quality of pilot training increases the flow of safety into the system. But we also know that the increasing safety of air travel was a major factor in increasing the amount of air travel, and that meant that the global aviation system needed more pilots. This demand for pilots trained rapidly had a negative impact on training quality, driving a decrease in safety in the system. This increase in the amount of travel also had another effect. It meant that the system needed more airplanes. And this had a few effects. First, it has a positive influence on the rate of technological advance, because more planes sold means more room to distribute the research and development cost. And by and large, these technical advancements all improve the quality and the amount of safety in the system. The increasing number of planes needed also created an economic environment ripe for consolidation because there were opportunities for cost saving and volume. This consolidation caused the dilution of Boeing's culture of engineering excellence. And the level of safety in the system contributed to it, making it feel safe for Boeing to dial back engineering excellence just a bit in the name of profit and stock price. And we know from earlier that this drove a decrease in safety. Third, the increase in planes needed in the market also increased competitive pressure. Boeing had to play catch up with Airbus, and that meant that Boeing had to increase the speed at which they designed planes. And we know that this is also partially influenced by the safety in the system. They felt safe speeding up a little bit because it's so safe, surely they can afford to go a little bit faster, right? We know this reduced the design quality, and that in turn decreased the overall safety of the system. And finally, from a regulatory perspective, the amount of safety in the system made it possible for the US Congress to tell the FAA to increase the amount of delegation they were doing to aircraft manufacturers in the certification process. This meant, among other things, that the FAA missed the change to MCAS, clearly decreasing the safety in the system. Now, if you stop and look at it, every feedback loop in this chart is rooted in the safety already in the system. So what does that mean? That the safety in the system caused the problem with the 737 MAX? Well, in a way, actually, yeah. In the Intro to Thinking in Systems, Dr. Meadows says everyone or everything in a system can act dutifully and rationally, yet all these well-meaning actions too often add up to a perfectly terrible result. And that's what happened here. Every actor in the system, buoyed by the safety of modern aviation, borrowed a little bit from safety to optimize something else: profit, speed to market, regulatory cost, pilot training speed. None of the participants in the system set out to build an unsafe plane or to cause a crash. But the growing infrequency of aviation accidents cause them to lose perspective, cause them to stop thinking about just how magical it is that we can take a machine that we have built, get it into the air, and in a matter of hours fly to another place. They stopped having the reverence for how dangerous that actually is, and let the margin of error in the system decrease to the point that there was a tragic outcome. So what should we as software engineering leaders take from this? Well, given we're at LeadDev, many of us likely have some familiarity with thinking in systems already. People tend to choose engineering leadership because they like debugging and optimizing systems. But how often do we actually make the time to stop and think holistically about any of the complex socio-technical systems around us to understand the behavior that we're seeing? We're so busy doing that we so rarely stop to observe and think. We unintentionally shortcut our way through understanding the full system, focusing instead on individual problems and their symptoms. And when we do this, we often miss the broader systemic reasons that something's happening. We might fix the symptoms, but in doing so, we often unintentionally make another problem somewhere else in the system worse because we didn't understand the full system that was driving the behavior in the first place. And that's what I want you to take away. You have to make time to slow down, to think in full about the systems around you, to understand them deeply, because you don't know what important things you might uncover when you do this. Some of the concepts most important to me personally, like human factors and resilience and generative culture, those things emerged from people who took the time to break down systems and really understand them, making the software world a better place along the way. If you want to get better at this, Dr. Meadows' book is a fantastic resource for learning formal systems thinking and how to use it. It'll help you get better at more accurately noticing and understanding the systems around you. And it'll help you build the tools that you need to be able to influence those systems and be more effective in improving them the way that you would like to improve them. And let me leave you on a positive note about the 737 MAX as well. One cool thing about systems is they tend to be adaptive and interested in their own survival, and that's definitely true here. In the wake of the two crashes, during the grounding of the MAX, a few things happened. First, the decrease in safety in the system caused the US Congress and FAA to rethink their approach to certification delegation. Specifically, manufacturers can no longer self-certify a novel or unusual design feature, a label that would clearly apply to MCAS. And the FAA now has to approve the individuals that manufacturers delegate certification authority to. They can't just pick whoever. And this should increase the safety in the system. The crashes also had an important impact on design speed and quality at Boeing, both directly and indirectly via changes to FAA delegation and certification scrutiny. 737 MAX was grounded for 1 year and 8 months. During the time that it was grounded, they found other software issues. They found electrical wiring problems. They found plenty of other things to fix along the way because Boeing took the time that it probably should have taken before it launched the plane in the first place to really get the design right. Crucially, MCAS can now only activate one time in a low-speed stall scenario, and only if the pilot and co-pilot angle of attack sensors are in agreement. This clearly increased safety in the system. And finally, the crashes pointed out that pilots actually do need simulator training to safely fly the 737 MAX, a positive impact on training quality, further increasing the safety in the system. Now, I have to address the elephant in the room before I can leave this stage, and that's that at least one of you in this room is probably flying home on a 737 MAX. And if that's you, I don't want you to worry. There's a really, because of the amount of scrutiny that this plane has received, because of the fine-tooth comb that Boeing and the FAA took to it during the 1 year and 8 months it was grounded, it might be the safest plane in the air right now. No other plane has gotten this amount of scrutiny in the modern era. I'm not flying one on this trip, but since writing this talk, I've actually flown the MAX 3 times. And it's a really lovely plane to fly. It's nice, it's quiet, and I really enjoy flying it. So if that's you, if you're flying home on a 737 MAX, you shouldn't be worried. It'll be fine. And as you go, best of luck digging deeper into the systems all around you so that you can influence them for good. You might even stumble across something important in your journey that makes all of our jobs easier. And if you do, I hope we'll see you on this stage in the future to tell us that story. Thank you.